Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture example 01 part E. Student, as we start this example in lecture 02 example 01 part A, in L02 example 01 part A, and we ends at lecture 02 example 01 part D. In part D we covered the detailing of this example, while in part B we covered the case 2, while in part C1, C2, C3 we covered these methods, and C4, and finally what we got in this example, the final design of this beam is 6 number 7 bar, which is my area of steel. It gave me an area of steel is 3.6 square inches. Now in the present lecture, which is lecture 02 example 01 part E, we will review this problem. This is the review of this example or analysis of this example. Here we will analyze this section which we finally design, right, which we finally design this section with the 6 number 7 bar, right, 6 number 7 bar with area of steel which is 3.6 square inches. Now the width of the section is 12 inches and the overall depth of the section is H, which is 30 inches. Now we will start the review of the problem. We have already recorded example 01 to example 05 in lecture 01. All these examples are the review examples. I will share the link in description so you can watch those examples, that how we can review a concrete section. As you can see here, to start a review problem, we are assuming that, let's say, our stress in steel equals to the yield stress. So to prove this assumption, we find out the value of epsilon s, and we compare that epsilon s with epsilon y. If my epsilon s is greater than epsilon y, so this assumption is okay. If epsilon s is less than epsilon y, so this assumption is wrong, right? Now as you are noting right here in this section, we are using 2 layers of reinforcement, so that why we need to find out the effective depth, which will be somewhat at the middle of the section, at the middle of the steel, as the steel is symmetry about the centroidal axis, because in the top we have 3 number 7 and in the bottom we have 3 number 7. So that why we don't need to calculate the centroid. Centroid lies at the center of these 2 steel reinforcement. Let's say these 2 layers of reinforcement is separated by a 1 inch dia bar. So let's say this is 1 inch distance. So my D will be, how to calculate the effective D, right? This will be 30 minus the square cover, this is 1.5 inch, minus the stirrup diameter, which is 3 by 8. So this is 3 by 8 minus the half of this bar. So this is 7 bar, divide by 8 to convert it into dia, and divide by 2 to half this bar in various part, and the actual effective depth is this much. So as from the previous discussion, we see that when your D value is decreasing, your area of steel is increasing, and if you are increasing your effective depth D, right, your area of steel is decreasing, right? This is a direct relation between area of steel and the effective depth. So as our depth is decreased right here, so if you, although the difference is very small, it will affect a little bit the area of steel. If we revise the area of steel and recalculate the area of steel for this depth, we will find the area of steel, which is, I think so, round about 3.33 square inches, which is close to our calculated area, that is 3.29 square inches. And already we are providing area of steel to the section, that is 3.6 square inches, which is well above than this value. So that's why this is a little bit difference, so therefore it not affect up to a certain limit. So our D value which will be used in our calculation will be this one, right? This value. So let us we calculate the epsilon S value, right? So to calculate epsilon S we need A. Let me calculate the A value, which is from this equation B, and we know A is, now this time we will plug the area of steel value will be 3.6 square inches, right? We have to use that value which we are providing to the section, right? FO is 60 KSI and we know all the values. A value will be 7.058 from this, right? We will calculate the C value. The C value will be A divided by beta 1. So from this beta 1 is 0.85, A value is this. So from this I got 8.30. This is my C value. Now I'm able to calculate the value of epsilon S. So the epsilon S value D minus C divided by C into epsilon U. We know all the values. D is 26.75, C value is this one, and epsilon U value is 0.003. So from this the epsilon S value is 0.006, which is well above than the epsilon Y value. Epsilon Y value is Fy divided by E, and if we calculate the epsilon Y value, this is 60 divided by 29,000 KSI, right? So from this 0.00206. So that why this value is more than this value. So that why this means that the assumption is right. The assumption is right. Epsilon Fs equals to Fy, and this we can say yielding is occurred. The steel is yielding. Now we will find the strength reduction factor, right? Now we will see whether the strength reduction factor phi can be taken as 0.9 or not, whether it need adjustment. So for this we need epsilon T. As we can see, we have two layers of reinforcement. That's why epsilon T is not equal to epsilon S. Now we need to calculate epsilon T, we need dt. So how to calculate dt? Let me show you this, how to calculate dt. dt is nothing, it is the center distance from this lower bottomest reinforcement center to the top, right? So this can be determined by 30 minus square cover minus 3 by 8 minus half of the bar. One thing which we need here, we must subtract. Noting this point, I forgot this point, sorry for this mistake. You have to subtract this half distance. Remember this half distance, because the vertical distance between the top and bottom layer is 1 inch. So that's why we have to subtract that half distance, and if you subtract this, you got this value, right? So please make correction for this, right? This is important. I forgot this point, so please add this point, right? To calculate dt, dt can be determined by dt will be 30 minus 1.5, which is clear cover, bottom cover, minus dia of the stirrup, minus half of the bar, right, which is number 7. So number 7 divided by 8, it will give me the diameter of the 7 bar, and divided by 2, we have to half this. So from this we got dt, and dt will be 27.687, right. One thing which will be noted right here, this 2 should not be included right here, okay. So that why we have to counter the whole bar diameter, not the half, right. So because we have to subtract this distance, right, this distance, so this 2 will not be counted, right. This will give us 26.75, right. This is important. Make correction for this, right. This is important. How to calculate d value, right. Now once we calculate the value of dt, we are able to find out the epsilon t value, right. So epsilon t from the proportionality dt minus c divided by c into epsilon u. From this we know all the values. We got the epsilon v value, which is 0.007, which is more than epsilon which is more than 0.005. so this means p is 0.9. this means this section is under reinforced, and we can take the p value is 0.9. now we are able to find out the md or phi mn. This time 0.9 times Fy, which is 60, times area of steel, which is 3.6, times d value will be 26.75 minus a divided by 2. So a value is 7.05. so 7.058 divided by 2. So from this I got the value for MD, that is 4514.16 kif inch, right. And if convert to feet, we got 376 kif feet, and this is well above the required MU, that is 352.4 kif feet. So this is a perfect design, because there is a little bit difference between these two. Always try and make sure that there is a little bit difference, because sometimes we design such a section that this value is far away than this one, so that will not an economical design, right. After this we will find the ductility check. So for ductility we will calculate the rho provided. Rho provided is area of steel divided by BD. Area of steel is 3.6 divided by 12 times 26 divided 26.75. I got here 0.0112. I have already calculated the value of rho minimum, which is 0.0033, and my rho max will be, I have already calculated this rho max in case 1, which is 0.0135. I have already calculated this, right, from the equation 0.85 Fc prime divided by Fy into 3 by 8. So I have calculated this rho max from this equation, and the value is this one. So we can clearly see that the rho P, which is rho provided, we can clearly see that my rho P is greater than rho minimum and less than row max. So this check is also okay. And I have already satisfied the S, provided that the spacing criteria is SP is greater than S minimum and less than S max. We have already checked this in previous part. This winds up this review problem here. See you in next lecture. Thank you for watching.